Lucas Dauger, who is speaking explicit formula for period polynomials.
Thank you. So Sujimura, do you hear me well?
Yeah, I can hear. Thank you.
Well, so yeah, first of all, I would like to thank both of the organizers for inviting me. It's a great pleasure to be able to speak here. So I'm going to give a very elementary talk, let's say, on that will focus on period polynomials of cusp forms. Here, everything will be with respect to the full modular group. So I will always consider modular forms and cusp forms of level 1, let's say. Keep in mind that everything can be extended in higher level, except for the explicit formula that I, for the moment, don't have for higher level cusp forms. Okay, so it will be divided in 3 parts. The first part will be just focused on giving a few basic definitions of period polynomials of cusp forms. Polynomials of cusp forms. Once again, for the full modular group. In the second part, I will just make more precise the link between period polynomials and pro-unipotent Grothendieck-Teichmüller theory by let's say, by explaining two precise examples of some applications that we find. So let's call it some applications. To Grothendieck-Teichmüller theory.
Excuse me. I can't hear the sound.
It's me that you can't hear?
Oh yeah, I can hear now.
Speak louder.
Yeah, I'll try. So whatever, I'm going to maybe show you guys the explicit formula at the end. It's not very important for the moment. So let's start with a few quick general review of period polynomials of cusp forms. So as I said, what I will consider is cusp forms for the full modular group. So I will only consider the action of SL2, or let's say PSL2, of Z on the upper half plane. And consider, let's say, classical holomorphic modular forms. So most of these objects have been defined in the previous few talks, but I'm going to define them as well. So modular forms. So a modular form is just a holomorphic function on H, which of a given weight K, let's say, which satisfies the following properties. So if we take a gamma to be a matrix in the modular group, Then we ask for all elements z in H to satisfy the following property. F of gamma of z has to be equal to C z plus D to the k f of z. And we also ask f to admit a Fourier expansion. Let's say at 0, so f of tau, for all tau, f of tau can be expressed like this. So the sum of a and q to the n, where q is the exponential tau. Okay, so the first condition can just be expressed as two small, simple functional equations considering any set of two generators of the modular group, and the second one just means that that f should be bounded, f of tau should be bounded as the imaginary part of tau tends to infinity. Okay, and I'll also call f a cusp form if its constant Fourier coefficient is 0. And here it means that f of tau tends to 0 as the imaginary part of tau tends to infinity. And so just a small notation. So as I will stay in level 1, I'll just denote by mk the space of weight k modular forms on H, and sk the space of cusp forms. And of course, the definition of the space of cusp form implies that it's an hyperplane of sk is an hyperplane of mk. Right. So we're going to consider a way to associate to every cusp form a polynomial. Let's say at the beginning with complex coefficients. So bivariate polynomials in two commutative variable, which is homogeneous with homogeneous degree k minus 2, where k is the weight of the cusp form, and which is defined like this. F is sent to the integral from 0 to I infinity. So let's take it along the vertical line of f of tau x minus y tau to the k minus 2 d tau. Okay, so one can see using the two small, so this is, as I said, this can just be seen as the fact that for, let's say, tau in H, f of tau plus 1 equals f of tau, and f of minus 1 over tau equals tau to the k f of tau. And applying these two conditions in the definition of R it implies the following basic facts. So if f is a cusp form, Rf, which is just defined by this polynomials, R of f will just be noted R index f here, satisfies the two following cycle conditions. So Rf of xy plus Rf of minus yx equals 0, and Rf of xy plus Rf of x minus y x plus Rf of minus y x minus y is 0. So these two conditions arise when we want to consider one cocycles of the cohomology of SL2 acting on this space by the irreducible representation of SL2 in GLD. And when we try to compute the space of cocycles that sends T, so this matrix to an element V minus the action of T on V. So that sends, let's say that sends T to V minus V point T for the right action of SL2. Yeah. And so I also use this matrix and this matrix. Let's say this one, minus 1, minus 1. Say this one. And so one can show that such a cocycle is defined exactly by picking the image of S, which should exactly be chosen as satisfying these two relations. That's why we call them cocycle conditions. Well, and so I'm going to just denote by WK the space of polynomials with rational coefficients of homogeneous degree K, which satisfy these two conditions. It's a subvector space of the space of bivariate polynomials of a given homogeneous degree. So now let's state the main theorem, which is due to Eschler and Shimura. So let K be an even integer greater than 2, and we consider R plus, which sends F, a cusp form, to RF plus. Here, plus just denotes the even part of this polynomial. So it exactly means RF of xy plus RF of minus xy over 2. So this induces an isomorphism. I mean a linear isomorphism from the space of cusp forms Sk to the space Wk, to the subspace of Wk given by the even parent polynomials. So here there is a small detail that we have to be aware of. It's not actually an isomorphism. It induces an isomorphism from Sk to an hyperplane of this space. So let's say to this space quotiented by xk minus yk. Let's put it like this. So let's just consider an hyperplane supplementary of this line in this space. One can easily see that the xk minus yk satisfies these cocycle conditions. Okay.
What was the plus?
Sorry?
What was the plus?
Oh, sorry. Yeah. So wk plus here means the space of elements p in wk that are even. So such that p of x, y equals p of minus xy. It's a subspace of wk, just, you know. We had one more condition.
So to be the question,
Oh yeah, you mean the ground field is yeah. So yeah. So the thing is that yeah. Exactly. But I can see, yeah, so actually one can show that this isomorphism can be defined over Q in the following sense. one can give a basis of the space of paired polynomials with rational coefficients, and that's what I'm going to do with. Yeah, thank you. Okay, so that's all for the basic things that I wanted to recall about the Shimura isomorphism. Are there any questions so far? No? So now I'm going to explain how these polynomials actually appear in pro-unipotent Grothendieck-Teichmuller theory, and I'm mostly going to focus on the double shuffle Lie algebra and more precisely on its associated graded, but keep in mind that the whole sequence of injections of Lie algebras that we saw many times in this workshop, that all the conjectures that I will state are actually made for every of these Lie algebra, which are conjecturally all isomorphic. So, yeah. So we had the double shuffle Lie algebra, which can be seen as a sub Lie algebra of the free Lie algebra with two generators. Just keep in mind that the Lie bracket is not the classical one. It comes from the Poisson bracket for the derivations of this Lie algebra. So this is the double shuffle Lie algebra, which corresponds to the dual space of formal multiple zeta values. Lie algebra. And so I'm just going to recall that the weights in this context always mean the homogeneous degree. So in x and y, I mean, and the depth of a given polynomial, of a given Lie polynomial x and y, will just be the y degree. So let me also recall that ds is graded for depths. Sorry, graded for the weight and filtered for the depth. And so one can consider its associated graded for the depths, which I will assume to be the linearized double shuffle Lie algebra today, which is still conjectural, I think, but yeah. So this is still a conjecture in I think depths higher than 3, isn't it? Well, yeah. And so there's the so-called Broder-Kramer conjecture, that gives conjectural generating series for the dimension of LS of a given depth and a given weight. Broder-Kramer conjecture. So conjecturally, the generating series of the dimensions of LS, which once again can be made for every of this associated graded, for every Lie algebras that we saw in this workshop, of a given depth. So D here is the depth, and N is the homogeneous degree. Let's say weight. Yes, and D is given by the following formula. So 1 plus ES T over 1 minus OS T plus S T squared minus S is T4. So here E of S equals S squared over 1 minus S squared, and O of S equals S squared S. Sorry, S to the 3 over 1 minus S squared are the generating series for the dimension of single zeta values, let's say even and odd single zeta values. And odd single zeta values. And S of S is also given by the simple following formula, which is S12 over 1 minus S4, 1 minus S to the 6, which is the generating series, let's say K, for the dimension of cusp forms for the formal diagram. So this is still very conjectural. This is proven only for depths 1, 2, and 3, and but I think that it's verified up to weight something like 30 or 35, something like this. So yeah, in this context, English is a pretty good language. When you don't have a proof for something, at least you can provide an evidence for it, and here's the case. So so if we look at this conjectural generating series, then one can see that some relation in the associated gradient of the double shuffle Lie algebra, some relations in bijection with the space of holomorphic cusp forms of level 1 should be observed in depth 2. That's actually what is already known and what is now called the Gangel-Kaneko-Zagier theorem. And one can also see that we expect to have some missing generators in depth 4 that we have to add to the classical ones, let's say the image of these generators in the associated gradient that Leila told you about in her talk. And so I'm going to make more precise this conjecture by stating the homological conjecture that describes, once again, conjecturally the homology groups of LS, which has been formulated by Brown. So at first, let me recall two small linear isomorphisms that will allow us to write the elements of LS that a priori are just elements of polynomials of two non-commutative variables as polynomials in a given number of commutative variables. So I will going to consider two of them. The first one is rho, which appears in some of Francis Brown's articles, which sends the depth d and degree n and weight n elements in the universal tensor algebra to to polynomials in d+1 commutative variables, y0 and yd. And it just sends the monomial x e0 y so on to x e d to y0 e0 yd e d here. Is this notation clear? So any monomial, any non-commutative monomial in two variable x and y can be uniquely determined by this way of writing it. And, yeah. So this is an isomorphism of vector spaces. And I'm going also to consider the ma-morphism, which comes from Ekal work, which does exactly the same, but the formula is not here is not the same. It allows us to be more precise on what should be the subspace on the right that corresponds to the Lie algebra, and also to have a very precise formula for the ER bracket on the left. So which is just the following: the same monomial is sent to U1 to the E. Oh, is it 0 minus 1 J to the E J minus 1. So I have to consider things that end in Y, right? Because is it the Lazare elimination? Leila, could you recall me the formula for ma? So I have to consider things that end in Y, right? So so it's an hyperplane of this space that I have to consider, and it's not the precise ma-morphism here. I have something to. Oh yeah, Sorry. Okay, so okay, let me be more precise for the morphism. Sorry. Yeah, thank you. So. Sorry, here? Yeah. Sorry? Oh, on the right. Yeah, yeah, sorry. So here, yeah, of course. Here we have n minus d. I think it's n minus d, right? Yeah. Yeah, it's n minus d. Yeah, thank you. Of course. Thank you. I'm only going to consider homogeneous polynomials in the space of commutative variables. Okay, so let me just add a few notations. So I'm going to consider add 0 of x to be defined by y, and for all n, add n plus 1 of x to be x bracket, let's say here, x brackets adds n of y. So the Lazare elimination theorem states that the space of non-commutative variables q on two variables x and y is actually the direct summand of the line generated by x and the algebra generated by all the adds n.
The Lie algebra.
Yeah, the Lie algebra.
No, it's okay. It's on the left.
Yeah. Thank you. And here.
Yeah, that's why.
For every n more than 0. Yeah. Thank you. And so the ma-morphism is defined on the Lie algebra generated by this infinite number of polynomials. 0 to the polynomials in D commutative variables U1, UD of homogeneous degree n minus d, and which here sends a word adds let's say y1 of x, so adds yd of x to u1 I1 minus 1 ud id minus 1. Is it here now?
Instead of x, you should be writing y, but it doesn't matter. It's
Yeah. It's just sorry. So it's you're right. Add x here. Yeah. Add x as y. Sorry. n to the power n plus 1, 1. Here it's just, yeah, thank you. So these are the two morphisms I'm going to consider. Here it's an injection, and we can exactly see what commutative polynomial come from the Lie polynomials, the subspace of Q to xy, which is defined by the Lie polynomials. And so I'm just going to write the same brackets, but with index rho and ma, let's say, for the era bracket, but seen as bracket on the commutative variable polynomials in this one, just pushing it forward. So how much time do I have left? Oh, is it? See. So we have, let me state the Gangal-Kaneko-Zagi set of relations. So I'm gonna state it this way. We have an exact sequence like this. So here's the set of even parallel polynomials that we are interested in to the exterior power of d1. I'm going to explain what it is. Then the bracket, let's say, with respect to rho, of course, it works for ma also. Yeah. And then the isomorphism rho in every column. So rho of plus minus 1 Okay, so what does it mean? It means that all the linear relations in depth 2 for the associated gradient of the double shuffle Lie algebra are precisely described by even paired polynomials of cusp forms. That's Is there any question? And so, yeah, sorry. Yeah, from WK to D1, D1. So if you consider all the morphisms from, sorry, all the generators we, Leila talked about 2 days ago, so sigma 3, sigma 5, and so on, and you consider the image in the associated gradient, yeah, then a paired polynomial P, which is just a sum from, let's say, 0 to k, lambda I x k is sent to the sum of lambda 1 sigma I sigma k minus I bar. That's this one. So here I should. So a parent polynomial is an alternate polynomial. Recall that the first defining condition just means that the first coefficient of the polynomial is minus the last one, and so on. So it's a polynomial of xi yk minus I minus xk minus I y to the I. Let me check. Yeah. So this is this injection here. Okay, so one last thing about the applications we have of paired polynomials in this precise context. Let me just state the homological conjecture made by Francis Brown. So we have let's say at least two ways to define linear injections from the space of paired polynomials of cusp, even paired polynomials of cusp forms to LS4. One is denoted by E, and the other one is denoted by D by Francis and by karma for Ekal's work. And so these, the image of this two morphism satisfy conjecturally the property of being the missing generators that we expect to have looking at the Brodel-Skarner conjecture. So let me state it precisely. Oh, sorry, conjecture. The first homology group of LS should be isomorphic to the vector space generated by sigma 3, sigma 5, and so on. They're class in Q. And also with the exceptional elements, let's say E of OK plus. Let's focus on this injective linear morphism, but keep in mind that every of these three morphisms should work. Yeah. And the H2 of LS should just be in bijection with the space of cusp forms. That just means that all linear relations that we expect to have are the Ganglion-Konikowski ones. And so we also expect that the H3 and so on are 0. 0 for I greater than 3. Yeah. So that means that this description of this Lie algebra in minimal is minimal in some sense. Yeah.
Sorry, this is I don't know
Yeah, this is the homology for the Cartan-Lebesgue complex. Yeah. So one can quite easily see that let's say this is the homological conjecture, and it implies the Brodel-Skarner conjecture. Okay, so I'm moving to the last part of this talk, and I'm going to give a very elementary way to obtain an explicit formula for these polynomials that we're interested in. Is there any question? So I'm still going to consider the right action of GL2 on the space of here, let's say, rational polynomials on a given even degree greater than 2, homogeneous degree, I mean. Just define as follows: A, B, C, D should act on a given polynomial just as P of xy is sent to P of ax plus by, cx plus dy. Okay. And now just some notations that will be quite important for this last section. So theta will be seen as the automorphism of I'm going to write it V n, that's just space of homogeneous and degree polynomials. Of the n to itself that send x to y and y to x corresponds to letting act this matrix on the space of polynomials, and let me call push the operator that sends a polynomial p to p of y minus x minus y, which corresponds to letting act this U matrix on space. Right. These are both isomorphism. The first one is of order 2. The second one is of order 3. They generate a group that is isomorphic to SO2. And so I'm going to in this section, I'm not going to speak about the space of cusp forms. I'm only going to speak about the space of paired polynomials of cusp forms. So be aware of the fact that now the notation Sn is just given for the, let's say, one eigenspace of theta. I call it Sn because these are the symmetric polynomials. So that's, yeah. An here will be the space of antisymmetric polynomials. And let me just make something more precise here. The space of alternate polynomials here, like antisymmetric and alternate will be the same here, corresponds to coming from the mamorphism, so coming from the Lie algebra, being an image of an element of the Lie algebra by the mamorphism. That's so. Let me call a push invariant a polynomial that is fixed by the push operator, and push neutral, a natural supplementary of this, an element that is 0 of identity plus push squared. Sorry for all the notations, just one more line. I'm also going to consider the intersection of all of the spaces. So basically, APIN is the space of alternate and push invariant polynomials, and so on. APN and SPN, SPI, and so on. Okay, so I will be interested mostly on this space, but we'll see that all of these four spaces are very similar one to each other. So, okay, first of all, yeah. So, okay, sorry. Here, this is AN intersection of, with PN here, and PN is just push neutral elements. It's just a notation, but yeah. So unfortunately, the operator push and the operator theta do not commute. So we here we can see, of course, that the space Vn is the direct sum of Sn and An, and it's also the direct sum of Pi and Pn. But because they do not commute, we a priori don't expect An to be the direct sum of API and APN. But this is the case. It's not so hard to prove, but they do not commute. It's still same here. SPN, S, N is the direct sum of SPI and SPN. This will be very useful for what we're going to do. Right.
Which space is A?
So now, thank you. We have. So let me just recall the definitions of being an element of alternal and push neutral polynomials. It's the space of P in Vn such that P of x, y plus P of y, x, this is theta of P, equals 0. This corresponds to be an alternal polynomial. And P of xy plus P of y minus x minus y plus P of minus x minus y x equals 0. And none of these spaces are the space of period polynomials, even the space of even period polynomials. But the interesting and useful result is that APN plus is now equal to WK plus. So once again, let me just say that APN is not the direct summation of APN minus and APN plus, and so is for every of these four spaces that we saw below, and then and APN is not WN, sorry, here, and yeah, let's say APN is not WN, so all the computations are quite hard to do in the WN side, but in APN some few basic results will help us to have an explicit formula. Is there any question? No. So because APN is the direct summation of, AN is the direct sum of API and APN, and so is for SN, one can expect that because 50% of the polynomials are alternal and 50% of the polynomials are symmetric, then so it should be the same for push invariant polynomials and also for push neutral polynomials, and this can be shown in many elementary ways. For example, let me state that API n corresponds to LS2 n plus 2, actually, I think. Yeah, n plus 2 in Ecal theory of moles. And okay, it corresponds to LKV2, but because LS2 is isomorphic to LKV2, and because the Browse-Kramer conjecture is already known in the depth student, one can just rely on this result to have the explicit dimension. So the dimension of APN is n minus 1 over 3. As expected, I would say it's the, so why do we expect this to be true? AN is of dimension n over 2. It's the 1/2 of the space of parent polynomials are alternal. And if, so push, the operator push doesn't stabilize the space AN, but because we have these two very useful identities, we expect 1/3 of alternate polynomials to be push invariant and 2/3 of alternate polynomials to be push neutral. So 2/3 of this is approximately what we expect to have for APN. That's the. And more precisely, so let's say here, SPI is the only. So now SPI in every degree, I'm considering SPI to be the sum of SPI n for all n, is a sub-algebra of C of xy, let's say Q of xy. Just because multiplying two push invariant polynomial will still be push invariant, and multiplying two symmetric polynomial will still be symmetric.
So no negative 比较关注 negative if 的体下。
Oh yeah. Sorry. So I'm in this talk. I'm mostly considering even degrees, but everything works in odd degree also. And so I can consider the sub algebra for n even. You're right, but it's still a sub algebra for n odd also. Everything works in Thank you. And actually, SPI is precisely equal to the algebra, the algebra generated by these two polynomials, x, y, x plus y, and x squared plus xy plus y squared. That's the. Why is it useful to know a basis of the algebra SPI? Because one can easily see that if we have, for example, a given alternal and push neutral or push invariant polynomial, and we multiply it by a symmetric push invariant polynomial, it will keep the properties of being alternal or symmetric and being push neutral or push invariant. So that's a way to act on. Sorry?
So not n. What am I mistaken?
Exactly. Now even. So even here and even here. Thank you. But no, not even here and even here. Well, yeah. Thank you. Once again, this works in every degree. I'm just mostly interested in even paired polynomials because that's because they appear in Grothendieck-Teichmüller theory, but everything works for odd polynomials also. Thank you. And so this basis allows us to give an explicit basis of APN of a given degree, which is now vects of xk, yk, x plus y to k, and x a minus 3k minus y minus n minus 3k. K equals 0 to n minus 1, 3. Maybe here n minus 3 shouldn't. Okay, let's know. Yeah, this should work. Yeah. And so it's now that we know that this algebra is generated by these two polynomials, and in particular just that this polynomial is a symmetric push invariant polynomial, then it's quite easy to see that APN, that all of these polynomials are alternal and push invariant. Namely, this polynomial is the one I gave you. No, APN.
All of these polynomials?
No. This one is by the previous line an element of SPI, and this one belongs to APN. This is the Eisenstein part of the, this is so. So we can extend the Eichler-Shimura isomorphism to the space, to the whole space of modular forms and compute the image of the Eisenstein theories, and then one finds that this term appears in the space of paired polynomials, and it's quite interesting. Actually, I stated the Eichler-Shimura isomorphism for cusp forms, and it says that the image of the space of cusp form does not contain the line generated by this polynomial. That's very important. Okay, so yeah, once again, this is clear. This is very easy to see that this polynomial is alternal. For example, this is symmetric, and this is alternal. So alternal bisymmetric is alternal, and this is also very easy to see that this polynomial is push neutral. All of these polynomials are push neutral. X to the something minus x to minus y to the same, and this is symmetric and push invariant. So the product should be in APN. That's very okay. And this family is clearly linearly independent. So well, this forms a base. Yeah. And so the important equality is the fact that APN has a priori no relation with Wn, but APN plus equals Wn plus. Actually, the two defining conditions of IPN really look like the two co-cycle conditions I gave you in the image of the Escher-Shimura isomorphism, but it's not exactly the same here, and we have to add the property of being even in order to define the same subspace. That's the point. And so because we have this equality in a very, very simple basis of this space, then one can compute. Let me state it precisely. An element R, which is, so let me call this polynomial Rk. R, which is a linear combination of Rk's from 0 to n minus 1 over 3 is even if and only if, and then we can just try to solve this linear system we obtain trying to cancel every odd term. But this is quite simple because okay, so let me state it precisely. If and only if lambda 0 lambda n minus 1 over 3 belongs to the kernel of the following matrix. J plus 1 to, let me check, to j minus a plus 1 minus j plus 1 n 2i minus j minus 2 for 1 I q 1 j q plus d, where q equals n minus 2 over 4 and d equals the dimension of the space of cusp forms. I'm going to write it sk of SL2 of z here to say that it's not the space of symmetric polynomials, but the space of cusp forms. Well, so this matrix is a full rank matrix. This is very easy to see when you try to write it down. The left squared part is upper triangular with non-zero determinant. So this allow us to give another elementary proof of the dimension of the space of paired polynomials, and we just have to solve explicitly this linear system corresponding to this kernel to obtain a very explicit formula. And maybe I'm just now going to show you the formula we obtain. This is just a small computation. So do I share? And this one should, yeah. Thank you. Thank you. Well, so we just defined some elements that will correspond to the linear combinations being in the kernel of this matrix, and then because the basis I gave for APN is not given explicitly on these elements, we just have to do a small correction in order to have an explicit formula for all. So this small correction to have the explicit coefficients in this polynomial that we expect to have for paired polynomials of cusp forms. Yeah. So let me just state one or two possible directions that we can take coming from this formula. So maybe this formula can help us. That's work in progress to show that the exceptional elements that we define for the homological conjecture are actually motivic. That's means that they actually come from the GM, the Joule space of motivic multiple zeta values. And another possible application of this is because we give a closed formula for the space of all periods of cusp forms of level 1, we're able we may be able, that is very, very work in progress, but to prove the conjectural causality of a model Lie algebra, which is conjecturally isomorphic to LS, which will imply that if the first two homology group that we saw in the homological conjecture are actually the H1 and the H2 of LS, then the H3 is automatically 0. it really means that this presentation of this Lie algebra is minimal in some sense. It's equivalent to be causal. And I'm going to stop here.
Thank you very much for your answer. Any questions, comments?
Oh, yeah, sorry.
Sorry, it's very simple. You mentioned this modular group in the beginning. I'm just curious.